In part 6 of the Unit 4 notes, we are going to be using what we learned about quantum numbers in order to write orbital notation diagrams. Orbital notation is a visual representation of the probable location of electrons with regard to the 4 quantum numbers. Each electron will be represented by an up or down arrow. The principal, angular momentum, and magnetic quantum numbers will be represented by labels under the boxes and the number of boxes. There are 3 rules or principles which will guide you in the filling of these diagrams. You can see an example of what an orbital notation diagram would look like for oxygen. Our first principle is Aufbau Principle, and this states that each electron occupies the lowest energy orbital available. In German, Aufbau means building up or construction. In reality, atoms are not built by adding protons and electrons one at a time, but this will help us to make sure that our electrons are in the correct location. So for example, if I only had a single electron and I was trying to place it within each of my orbitals, it will want to fit into the electron that is closest to the center of the atom, so the lowest energy orbital, and I would start by placing it as a spin-up electron. This is very similar to how we have been filling in our Bohr models. For our first checkpoint, if your teacher were to hypothetically allow you to choose the type of assessment you were to have at the end of the unit, which of the following options would you choose? All of these assignments would be worth the same number of points, so the potential options are to complete a word search containing 10 words, to read 15 pages in a textbook and answer 10 questions, take a 40-question long closed notes test, or write a 60-page lab report with citations. Now, if all of these are worth the same amount of credit, most students would probably agree that completing the word search would be the most efficient use of their time, and they would most likely get a good grade on that. So they would like to choose this. But if one student is being particularly annoying and I decide that that is no longer an option, the one that you would most likely select after that would be the next easiest, likely to read the pages in the textbook while answering a couple of questions. And if that is no longer an option, then you would move on from there. And that's basically what is happening with the electrons inside of the atom. They want to do whatever is easiest for them first. So they would go closest to the nucleus within their shells, and when that is no longer an option, they would go to one of the orbitals that is further away. So that's Aufbau Principle. Here we have an orbital notation filling diagram. On the left side, you can see each of our designations going up based on energy. So we start with the lowest energy, which is 1s, and then 2s, 2p, and so on. When you get to a specific energy level like 2s and 2p, you can see that the p orbitals are slightly higher in energy than the original s orbitals were. But once you get to the p orbitals, all 3 p orbitals are the exact same energy, so they are identical to each other. The same is true for the 5d orbitals and also for the 7f orbitals. It's a little bit easier to see along the side here where things would be filled into next. You might notice that there are a few anomalies within this chart. You would think that you would fill in all of the 1s, all of the 2s, all of the 3s, and then all of the 4s. But you can see right here that the 4s is filled before going into the 3d. That is because there are 2 factors that go into the amount of energy that an orbital has. The principal quantum number, which is the number out in front, but also the shape of the orbital itself. Because a d orbital is a much more complicated shape than a sphere, a 4s orbital overall is actually slightly less energy than a 3d. So this orbital would be filled in first before moving on to the 3d. So you would be able to look at a chart like this in order to determine which orbital is going to be coming up next. Now, while this part on the side tells you what orbital is coming up next, it doesn't tell you how many orbitals would have to be filled in. Now, you could simply memorize it because it's relatively simple. All of our s orbitals only have 1, our p orbitals have 3, d have 5, and f have 7. So 1, 3, 5, 7, going up by odd numbers. You could also simply look at the right side of the chart here, and it tells you how many boxes you would have to fill in for your diagrams. The diagram on the right is basically the exact same thing, They do show you your differences for energy levels. So you have 4s and then 3d and then 4p. That same anomaly you can see up above here as well. So as you're going through the s orbitals for the 5th energy level, you go 5s, 4d, and then 5p. And you see something similar up here with the 6s. So 6s, and then all the way to 4f, then 5d, and then 6p. There's also another type of orbital notation filling diagram known as the diagonal rule. And if you were ever asked to try to memorize how these would be filled in, this would probably be the easiest for you to try to recreate. All you have to do is fill in from 1s down to 7s, and then each time you move over to a new letter, you go down by 1. So if I started with 1s, then I'm going to start with 2p, and then 3d, and then 4f. And you just draw arrows through each of the different numbers. You follow the arrows as you're trying to fill things in. So I would fill in with the 1s first, and then the 2s, then the 2p, 3s, 3p, 4s, 3d, and so on. And you can see how even with this rule, it shows you that after the 4s, you would then go back to fill in the 3d. Now, the one negative to this type of diagram as a method of filling in the electrons is that it doesn't tell you how many orbitals you have for each one. So, like I said on the previous slide, all of our s's there are 1, p there are 3, d there are 5, and f there are 7. So for that part, you would have to remember it. Our next rule or principle is the Pauli exclusion principle. And this states that a maximum of 2 electrons can occupy a single orbital, but only if the electrons have opposite spins. In other words, no 2 electrons can have the same 4 set of quantum numbers. The first 3 numbers deal with the orbital itself: energy, shape, and orientation. The last deals with the electron spin, which is a positive or negative 1/2. I often consider this the postal address rule. So you might have the same exact numbered house as one of your friends. Maybe you both have a house number of 10, but you would have to live on different streets. Or maybe if 2 people both live at 10 Main Street, they live in different towns. So one part of the postal address always has to be different. And the same is going to be true for each of our electrons. If I have 2 electrons that are both in a 1s orbital, well, one has to be spin up and one has to be spin down. If I have 2 electrons that both happen to be spin up, well, maybe one is in a 2s and the other is in a 2p. So something will have to be different about each electron so that they have their own postal address. Our final rule is Hund's rule, and this states that electrons of exactly equal energy, same principal energy level, and also the same shape, are each occupied by 1 electron before any orbital can take a second electron. When all orbitals of equal energy are filled, then a second electron of opposite spin can enter. So what this means, let's say that I am filling in the second energy level. The 2s is slightly lower in energy than the 2p. So my 2s has to get filled in up and then down before moving on. Then I fill in an electron into the 2p. But the electron would rather be in its own orbital if it's at the same exact energy level. Think about if you have a couple of siblings. If you can each have your own rooms, that would probably be preferred as opposed to sharing. So these electrons will each get their own room first. As we continue to fill electrons into these orbitals, if I move down here, if I no longer have enough space, so all 3 of these rooms are now filled, well, now somebody will have to start to double up. So now we'll go back and have an electron spinning down in the 2px orbital. So to summarize this rule, if you are at the same number and letter, so for example 2p, your electrons should be spread out first before you start to double them up. That's Hund's rule. For our checkpoint question, we are going to use what we learned in order to write out the orbital notation for these 3 elements. The first thing that we need to do here is figure out how many electrons each of these elements has, and we can do that based on the periodic table. Magnesium has 12 electrons because its atomic number is 12. Chromium has 24 electrons, and nitrogen has 7 electrons. Next, we would use an orbital filling diagram like the one that I have right here in order to fill in my spaces. Magnesium, I'm going to start with the 1s orbital. Each one of my orbitals can fit a maximum of 2 electrons. I can fit an arrow spinning up, and since there's no other orbitals to spread out into at the 1s, my second electron is going to spin down. I've now used 2 out of my 12 electrons, I have 10 left. After my 1s orbital, I go on to the 2s. So I'm going to fill in a 2s line here, or a 2s box. Arrow spinning up. Now for my next electron, I can't spread it out into the 2p orbitals yet. I would have 2px, 2py, and 2pz for my 3 orientations, because it's not exactly equal energy. While these are all 2s, a 2s is slightly lower in energy than a 2p. So I'm going to fill in my electron going down before I move on to the next part. Now once I get to the 2p orbitals for electrons number 5 and beyond, I need to spread out my electrons before I double up. So this is 5, 6, 7, 8, 9, 10. Now you might be thinking to yourself, well, why did it really matter? Because they ended up getting backfilled in the end anyway. And to answer that, it's because eventually you're going to get to a point where you stop before the entire 2p orbital is filled in. And if you don't do it by spreading out the electrons first with Hund's rule, you're not going to end up with the right diagram in the end. All right, at this point I've used 2, 4, 6, 8, 10 electrons. I have 2 left. Next up after the 2p would be the 3s orbital. That 3s orbital can hold both of my electrons, so this right here would be the final diagram for magnesium. Now for chromium, I'm going to continue on from here. So I have 24 electrons. And since I just filled in 12 electrons, I know that it's going to start out like that and go beyond. So I'm going to fill in this part pretty quickly. We have 2px, 2py, and 2pz. And even though I know I'm going to fill completely through the 2p orbitals, just because of the muscle memory, I'm going to spread out before I start to double up to make sure that I'm practicing it the right way. After that, I would fill in the 3s, and I've now caught up with my 12 electrons. And I'm going to go beyond that because I want 24. After the 3s will come 3p. So I have 3px, 3py, and 3pz. Spin up, spin up, spin up, spin down, spin down, spin down. So I still need to fill in more electrons. Next up, I'm going to fill in the 4s orbital. Spin up and then spin down. So at this point, I've used 20 electrons, and I've gotten to this point in my filling diagram. The next orbital after the 4s is the 3d, and there are 5 of those orbitals, or 5 orientations. So I need to fill in all 5 of those lines, even if all 5 of them are not going to be used. Now the 3D orbitals do have actual X, Y, and Z designations, but they all fit in between the different orientations, and their designations are kind of complicated, so I am not going to make you memorize those. So you could just label these as D1 through 5. Now I've used up 20 electrons so far, I only have 4 left. And because these are the same exact energy level, the same number and the same shape, I need to spread those electrons out before doubling up. Now the fact that this chromium has 4 unpaired electrons spread out throughout the 3D orbitals, that's going to tell us something a little bit later on down the road about the types of properties that chromium would be expected to have. So the reason why we are drawing these orbital notation diagrams is because they will help us with the properties of the elements later on. All right, for our final example here, we have nitrogen. Nitrogen has 7 electrons, so this will be considerably smaller than what we had already drawn. I can fit 2 electrons in my 1s orbital, 2 electrons in my 2s orbital, and now I have 3 electrons left. Next up, I know that my electrons are going to fit into the 2px, 2py, and 2pz. So I have 3 p orbitals. I need to spread out before doubling up due to Hund's rule. And now this is my completed diagram. So I have 3 unpaired electrons within my highest energy orbital for nitrogen. That concludes part 6 of the Unit 4 notes. When we come back for part 7, we will be writing out electron configurations.